Hi, everyone. It's Dr. Lindner. Okay, we're still looking at blood. And in this next short video, we'll talk a little bit about the lifespan of an erythrocyte, right? All body cells and tissues, they live for a certain amount of time, then they die, and the body makes new ones. Sometimes it gets recycled, some live longer than others. Bone is always being made and broken down. Skin is always being broken down and made. Hair is broken down and made. Red blood cells are broken down and remade. So here is the uh, average lifespan and expectancy of a red blood cell. It's about 120 days. Looks like it's about a season, right? Close to a season. It's 4 months, 4 months worth. So as erythrocytes age, like an individual, they become less flexible. The body becomes a little stiffer. So the cell membranes become a little bit more inflexible. And that's partially due to the oxidation of cellular components. And that's why antioxidants are so important to eat and consume, is because it helps to negate the effects of oxidation. So the membranes become inflexible and they rupture as they attempt to squeeze through the small spaces within the body, including the liver and the spleen. The majority of the erythrocytes, they rupture as they try to pass through the tissue spaces, including the spleen and liver. The average diameter of a red blood cell is about 8 microns, while the average diameter of the tissue spaces in the spleen are like half that. It's 3 microns. So as that red blood cell, the erythrocyte, attempts to squeeze through the tissue spaces of the spleen, the older, less flexible ones are going to rupture. And there is evidence that suggests that the nutrients that act as antioxidants can increase the lifespan of red blood cells. So this picture here on the top here at 12 o'clock, it says red blood cells are in circulation for 120 days. Okay, then what? Well, number one, the red blood cell dies and it goes through phagocytosis. So when the red blood cell ruptures, let's say it's going into the spleen and it ruptures as it goes through a blood vessel half the diameter, it's going to break up into its components. Well, it can break up into heme and globin, hemoglobin. Well, what happens to the heme? Well, some of that heme becomes biliverdin, and biliverdin can be converted into bilirubin, which goes into the liver. And the heme, which is iron, is transported into the liver. Iron by itself, it's not going to be transported. Iron is transported as it hooks up to a transport protein called transferrin. In the word transferrin, we have Fe, or it looks like ferritin, right? Iron. So when the iron is attached to transferrin and it's brought into the liver, it's now stored as ferritin. And this is important because this is like having money, which is iron. You're having money and you're putting some in the bank to store it. And this is why when people get their blood checked, it's important to get your iron checked, but also just as important to get ferritin checked, so we can see how much iron you have in circulation, but also how much you have in storage. We see a connection to decreased iron with anemias. We see decreased ferritin also associated with anemias. We see decreased ferritin with hair loss, especially after COVID, because these viruses thrive on iron. It just chelates them and eats it all up. So we want to make sure that when we're checking for iron, we just don't look for serum iron. We also want to check for how much is in storage. And that storage form of iron in the liver is called ferritin. Okay, so heme is transferred to the liver by way of transferrin. It's brought into the liver. Now we have ferritin. And look what happens to ferritin. Again, ferritin can be transferred by this transfer protein into the bone marrow where iron could be stored, plus globin, their vitamin B12, right? So everything's kind of hanging out and storing in this bone marrow. Well, globin can be broken down to amino acids. Those amino acids can be reused for protein synthesis. If we look at this bilirubin, right, the heme can be broken down to biliverdin, which is converted to bilirubin. That bilirubin can also be stored into the liver. And now the bilirubin can be pushed out into the small intestine because there's a connection from the liver into the duodenum. So from the liver into the duodenum, into the small intestine, bilirubin could be converted into urobilinogen, which is converted into urobilin, which helps give urine its color. And urobilinogen can be converted into stercobilin, which is what gives feces and stool its color and odor. Okay, so we start to see that the body can eliminate through urination, through bowel movements, a lot of the breakdown products of blood, but a lot of it can also be stored. And if it's stored, well, the kidneys can produce EPO. The kidneys can produce EPO or erythropoietin, and erythropoietin can go into the bone marrow to stimulate erythropoiesis. And with all of these ingredients, iron, globulin, B12, and that erythropoietin, we can remake brand new red blood cells that live for another 120 days, and then it can go through that cycle all over again. So erythropoiesis is the production of the red blood cells. It begins in the red bone marrow. Erythropoietin, that's the hormone that's released by the kidneys in response to hypoxia. Hypoxia just means lowered oxygen levels. So since a lot of blood, all the blood is going through the kidneys to be filtered, it's the perfect organ to say, hey, what is our oxygen levels like? And if they're hypoxic, then erythropoietin is pushed out by the kidneys, goes to the bone marrow to push out more red blood cells. If there's more red blood cells, then there's more cells that contain hemoglobin, more cells holding on to iron, more cells that could potentially bind onto oxygen. Okay. Reticulocytes, these are immature red blood cells. We said these are in circulation for a very, very short period of time, maybe 24 hours, at best 48 hours. So here's the erythropoietin mechanism. If we have an imbalance, then, or it's low, right? If oxygen levels are low, we have hypoxia. Hypoxia due to either a decreased red blood cell count or decreased amount of hemoglobin, or just decreased availability of oxygen, maybe high altitudes. Whatever the stimulus is, the kidneys are detecting a reduced amount of oxygen. So the kidneys are going to release erythropoietin. The erythropoietin is going to go to the bone marrow. The bone marrow has all those proper ingredients that's going to enhance erythropoiesis, which increases the number of red blood cells so that we have the increased ability to carry oxygen, and then oxygenated tissues increase. With the oxygen being driven to the mitochondria, more ATP. So for erythropoiesis to occur, we need proteins, we need fats, we need carbohydrates, we need iron, we need B12, we need folic acid, which is B9, and we need good vitamin E as well. The body stores iron in hemoglobin, 65% of that. We store it in the liver. We can store some in the spleen and in the bone marrow. In the liver, we called it ferritin, okay? Intracellular iron is stored in the protein iron complexes, such as ferritin. It gets stored as hemosiderin, but hemosiderin is a little bit more toxic. It can do a lot of damage in blood vessels and lead to cardiovascular issues. Circulating iron is loosely bound to a transport protein called transferrin. So let's not confuse transferrin, which is a transport protein, with ferritin, which is a storage form of iron inside the liver. Okay. Iron toxicity can occur in individuals who have high dietary intake of iron, or when a person is receiving multiple blood transfusions. When the stores of apoferritin have been saturated with iron, the body stores the iron in the tissues in a form of a substance called hemosiderin. Not ferritin, but hemosiderin. And a buildup of hemosiderin in tissues, primarily the blood vessels, can result in cardiovascular disease. One of the early symptoms of iron toxicity is going to be constipation. That's why when people take iron supplements, they're kind of reluctant to, because they think it's going to constipate them, but they do have non-constipating forms. And it can also cause black tarry stools. There are certain people who have hemochromatosis, which is a genetic issue in which they just have high amounts of iron within their body. They have to be very, very careful, especially with vitamin C intake. If someone is anemic, let's say, and they have decreased iron, vitamin C can enhance iron's absorption. But if you have too much iron, you want to be very, very careful with vitamin C supplementation. When I come back, we'll talk about different types of anemias.